So today I'm going to talk about generalized set theories and, which we have implemented in Isabelle HOL. And a generalized set theory is just a very big type crammed full of all sorts of stuff you might want for doing mathematics. And I'm Kieran, and this is joint work I've done with Joe Wells at HOL here. So when we're working in Isabelle HOL, all of our math objects are organized into lots of different types. So pi is type real, we have pair types, and we also have function types and stuff like that. But what if we don't want this kind of organization of all of our math objects? What if we want to be free from the whips and chains of your type system? So you could work in Isabelle ZF, where all of your math objects are implemented as pure sets, which live within one big type, D. So for example, our membership relation is just has this function type which goes D to bool. It's just a binary predicate on that type, and you say, oh, it satisfies my ZF axioms. And then we define natural numbers all as sets using, von Neumann encodings and stuff like that, and our other pairs using the Kuratowski encoding. But so then, in this case, most of our objects just have the same type. Everything is just of type D. Other than, of course, things which are too big to be of type D, like the membership relation and the power set operation, which necessarily have to have higher types. So when we have everything of the same type, we obviously lose the niceness that the type system gives us, which keeps track of the meaning of everything. So we could keep track of the meaning using soft types, which are just predicates on the domain, which we can write in a nice type-like notation and only define soft types for things that are type-like. So for example, the empty set and this pair both have the same type, they both live within the domain, but they have different soft types. So you can just have base soft types like set, you can have soft type constructors like a star one, which constructs soft types for pairs. Say thing on the left is of soft type 0, thing on the right is of soft type nut and soft type nut. And then we can also have soft type constructors like set of, which says that something is a set of some soft type, and arrow types for higher order functions. So this says that the power set operator takes, that's the wrong way around. That should be, the power set operator takes a set and gives you back a set of sets. Sorry, that's a typo. But of course in ZF we have representation overlaps. That is, you have non-empty intersections of soft types. So of course in ZF everything is a set, so you know that the set intersects with every soft type you could possibly, the set soft type intersects with every single soft type you could imagine. So how do we find a middle way in between these two options? Generalized set theories, which are just HOL specifications of axioms that avoid your type system awkwardness by stuffing all of your math objects into one domain type D, like you would have in ZF. They avoid the representation overlap by having sets, functions, numbers, pairs, all as distinct objects. And also, they allow support for partial functions and undefiners by having a special exception object, boom, which lives inside the domain, which you can use for undefined results like dividing by 0 and stuff like that. And also we have that, like, boom can't be inside any set or any pair and things like that. So we do this by mixing and matching what we call features for different kinds of math objects, so sets, pairs, ordinals, functions, and we also ensure, we have extra axioms that ensure a partition on the domain, so that's how you have everything distinct. And as an example, finally in the last minute, we can define, so this is something we can do in a GSD, we can overload subtraction so that it works on natural numbers and functions, which are both of the same type on numbers, and our functions all live within this domain. So, if n and m are natural numbers, then we want that if n is greater than n, then n minus m is just normal subtraction. Whereas if n is less than m, then it's going to be, boom, it's somewhat undefined. However, if f and g are functions from naturals to naturals, then we want to do sort of pointwise subtraction on those functions. So we want to get back a function f minus g such that when you apply that to any natural number, it's the pointwise subtraction on it. And then also you can, if you want to type, if you want the soft type to describe this operator, this subtraction operator, we could perhaps define a maybe soft type, which says that if your thing is not the exception, then it's of type P, and otherwise it's the exception. You could give a crazy intersection type for that subtraction operator if you wanted to do type-based reasoning about it. And that's it. Cool. Thank you.
Thank you.
Can you just
All right.
go back to one slide you had before? Yeah, because you usually disconnect, but I want to refer to something. How do you, I'll get back one more.
Oh, sure.
Okay, most math objects live in a single domain type D.
Yeah.
So do functions live there?
Yes.
Okay.
Well, it depends what you mean by functions. So we have sort of two concepts of functions. So obviously you have your like HOL functions. So you could call power set operation a function if you wanted to, because it still has a sort of functional property. It maps things in the domain to things in the domain, but it can't exist as an object within the domain because it would just be too big. It would cause paradoxes if that thing lived within the domain, because then you could take sets of it and stuff like that, and nasty things would happen. So some things necessarily have to have higher types, whereas there is a whole domain of functions which live in there, which are primitive, which basically correspond to all of the functions that you can build as sets of ordered pairs within your theory. So there's a correspondence between those two representations. Cool. Any other questions? Yes.
So, okay, correct me if I'm wrong, but you are like throwing a bunch of axioms, right?
Yes.
How do you know the whole thing is?
Because we build models of everything. We have a special technique that allows you to build a model of a GST within another GST. So you can do all of this all the way back to ZF. So you can live in ZF and then build a model of a GST with extra pairs and extra functions and stuff like that. Live in that, and then if you want to, you can build another model in that, and then jump into another GST, and then and we do all of this in Isabelle as well. Basically, by building a model, which is a portion of the domain, then performing a subtype definition in there to get this new type. So yeah, you're adding all of these extra axioms, but obviously you want to make sure that that's safe, and yeah, that's why we build the models. Cool. Thank you so much. Oh.
Okay. Well, I think we're sort of running over, so let's thank you all again. And, of course, we have more than half of the summer school ahead of us.